Okay, so welcome everyone to our final class for EES 129-229 entitled Designing Your Space Mission. I am Assistant Professor Miki Nakajima in the Earth and Environmental Sciences and Physics and Astronomy at the University of Rochester. So let me start sharing my slides. Okay, can you see it?
Mm-hmm.
Okay, great, thank you. So in this class, we have been learning previous, current, and future space missions and how to design your own space mission. Our students have been doing research on their own ideas, and we are looking forward to sharing their ideas today. And we have a fantastic review panel in today's presentations. Program specialist, Iron Damasi, is from the Rochester Museum and Science Center. And Aaron has an extensive experience in science, education, and communication. Dr. Elizabeth Frank is an applied scientist in first mode, and she provides scientific expertise in technical project management on space missions. She also recently hosted a panel discussion on how to lead a space mission. So I highly encourage you to check out her website. And Elizabeth was also extensively involved in the messenger mission. Professor Kevin Lewis is from the Johns Hopkins University, and he is extensively involved in the Mars Science Laboratory mission. His recent exciting work includes estimating Martian bedrock density by recalibrating the Curiosity's accelerometers. Professor Judith Pfeiffer is from the University of Rochester, and she developed the infrared array camera for Spitzer Space Telescope, and she's the mother of infrared astronomy. She's now involved in NEOCAM and NEOSUM mission. Dr. Kelsey Singer is a planetary scientist at the Southwest Research Institute and has been extensively involved in the New Horizons mission. And her recent exciting research involves craters on Pluto and Charon. She's also a recipient of the Urey Prize, which is a very prestigious prize in planetary science. And thank you all for coming, and we are very honored to have you all. Okay, great. And today's presentation is also supported by the Rochester Museum and Science Center. So due to COVID-19, unfortunately, the museum is closed, but there are wonderful virtual programs at the museum. Ivan, would you mind describing some of the ongoing programs?
Sure. So those of you who are from the area might be familiar with the Museum and Science Center. If you're not familiar, if you do get back to campus at any point soon, it's definitely worth checking out. Mostly what we do is we work with families and teens. So we have a lot of programming designed for young people as well as just the general public. And our goal is to build an interest and a passion for STEM topics. And because we also have the planetarium on our campus, we're very invested in building an interest and a love for space exploration and space travel. So right now during the pandemic, most of our programs are suspended, but we do have a virtual classroom set up. We have virtual planetarium shows. And we're planning a virtual camp fair for some of our younger patrons in a few weeks. So I'm mostly here as just a member of the public who works with sort of ordinary people who are interested in supporting space exploration and space travel or have an interest in it. And I'm really excited to see what you guys have come up with for today and how we can share that love of science and space exploration with the public. So thanks for having me.
Okay, thank you so much, Iran. So this is the list of mission proposals today and the team members, and I'm very excited to hear about their ideas. So today, each group will give a 60-minute presentation followed by a 4-minute Q&A. And during a Q&A session, we will first take questions from the panel. And if we have extra time, we will take questions from anyone in the meeting. And Scott Hall, who is one of our great class TAs, and the other one is Stephen, will let you know at 12 minutes, 60 minutes, and 20 minutes. Thank you, Scott. So, okay, so the first presentation, it will be given by the team Jupiter. So let me stop sharing my screen. Great, so the stage is yours.
Great, thank you very much. See if I can do this. Excellent, so thank you very much for having us. I guess we'll do our introductions first. My name is Evelyn Furwalt, and I'm an electrical and computer engineering student.
Hello, everyone. I'm Joe, engineering student.
Hello, everyone. My name is Mohammed Ba. I'm majoring in international relations.
Hey, I'm Colby Gervais. I'm a geological science major.
And we'll be presenting the Hercules-J presentation, which is regarding our second Jupiter orbiter. This is our proposal for basically Juno Part 2. So our primary mission objectives will be observation, measurement, and photography of Jupiter's moons, mainly focused on the moon Io. Apparently there are all sorts of volcanic things happening on Io that we think are very interesting. As well as, I think it would be very interesting to do more research and development deeper in our solar system. The more information we have about things orbiting Jupiter, the more R&D we'll have that will maybe open the door for a satellite network that can be made around Jupiter. In addition, the Great Red Spot on Jupiter's surface has allowed a lot of new information about the way planetary, like when you're observing the surface of a planet, you can learn a lot about its atmosphere. And I think if we understood everything there was to know about the Great Red Spot, we would learn a lot more about the way we could understand atmospheres of planets that are a lot further away.
Yeah, so the expected outcomes of this mission is to first successfully launch a flyby around Io and Jupiter. I would say there could be some difficulties around the way, and we have to account for those. But overall, we can just successfully get a flyby around Io and Jupiter. That is what is expected to happen. And we want to take further photos of Io and Jupiter with enhanced imagery that we can have today that the past missions didn't have. We would like to learn more about what makes Io an active moon. Io is one of the most active bodies in our solar system, and it's very interesting because there's not too many active bodies in our solar system. So learning why Io has volcanic activity and how it is active would be very interesting to compare it to Earth and see how different ways a planet can become active. We also like to learn more about Jupiter's red dot and why it's there as compared to what E just said. And I would like to use all this useful information to deploy a satellite network out there to assist further space exploration deeper into our solar system and possibly learn more about the farther bodies out in our solar system, such as the Kuiper Belt, and then maybe even out to the Oort cloud. And I believe a network around Jupiter would greatly enhance discovering, just exploring more about our solar system.
So this is going to be the second orbit to Jupiter, and the first was a mission called Juno. And the primary mission of Juno was to study the atmosphere around Jupiter, including how much water is contained. And then orbit Jupiter, and then map the magnetic and gravitational fields.
Your mic's cutting out, Joe.
How about, can you hear me now?
Yeah, you sound good.
Okay, perfect. Sorry about that. And then mapping the magnetic and gravitational fields would also help provide insight on how Jupiter formed and yes, and then but Hercules-J, the secondary mission, the primary focus will be on the moons of Jupiter, and then it would also try and set up a deep space communications tele network that would be Jupiter centric. So we test that out, and hopefully with the exploration of space, this would be a stepping stone for deep space communication.
So on our satellite, I looked into a lot of information about the way Juno communicated with us back here on Earth. It turns out in order to be able to communicate for that sort of distance, for that sort of length of time, you need 4 different sort of categories of antennas. You need a high gain antenna that will be working when you are the furthest away from Earth, when you're actually in the Jupiter orbit. When you're on your way, you need a medium gain antenna. This is used as sort of a medium high frequency. When you're close to Earth during launch or during the flyby, which we'll talk about later, then you can use sort of a low gain antenna, as well as during your initial burns, then you're probably going to use a super low gain antenna that's very specialized for that purpose. So here's a diagram of Juno, and you can see these 4 different categories of antennas and where they sort of sat. This big one is the one that will be used to come from all the way from Jupiter. So I don't propose that we just copy and paste Juno, but I do think that if this is what worked on Juno in order for us to be able to communicate with it effectively and be able to understand all of the readings and measurements that it's receiving, then we're going to need the same sort of architecture. Probably some measurements, some updates since we have more technology since when Juno was released. But yeah, that's the main idea.
So in order to come up with the power space, we take into consideration 4 sources of power, which has to do with the battery source, the solar panel source, the radioisotope generator source, and the fuel source. Due to the genuine interest of this mission, we decided to go with the solar panel source. But in so doing, we decided to consider 2 of those sources, which is the RGE and the solar power source. The solar power source is the farthest robotic traveler to run on the sun. It has a solar generation of 14 kilowatt per electricity. It is highly energy efficient. And for the RGE, it has a long-lasting lifespan, requires high temperature and efficiency, and it also powered by radioactive decay. Having considered these 2, this mission, we are recommending that this mission should go with the solar panel source because the solar panel source converts light from the sun into electricity, and it is going to be operating on the inner solar system by relying on the use of photovoltaic solar panels to derive electricity from the sunlight. The first ever spacecraft to have used a solar panel was the Vanguard 1 satellite, which was launched by the US in 1958. Next.
Yeah, so this is our expected launch date if everything goes according to plan. With the Hercules-J. The yellow down the middle is the sun, the blue orbit is Earth, the yellow or the green is the trajectory for Hercules-J, and then the orange is Jupiter. So this would be the expected date for the first one. As you can see, it's a great distance, and Jupiter's orbit is very large compared to Earth, so there's like very specific time periods where we can only launch the Hercules-J. So it's pretty important we stick to schedule, but if not, we do have other select dates we can move to. Next slide. So this is how the spacecraft will advance. You can see the green circle on the green trajectory is where the orbit will be by this time period. And next slide. So then by November 22nd, 2031, we should have the payload and Jupiter coming close together. This will allow us to prepare for operations that are occurring so we can we can get ready to explore Jupiter, take a more advanced imagery. We can get ready to CIO and learn more about that moon. And in case the dates don't work out, as they usually don't with space exploration and these types of projects, we have alternate cases delay, such as March 2nd, 2028, and then it would arrive June 7th, 2033. So as you can see, that's a pretty big difference as expected for this type of orbit, because Jupiter's orbit is so much greater than Earth's, and we don't want to waste unnecessary fuel, and that would greatly increase costs. So it's important that we stick to our timelines and our dates so we can reach our objectives and complete our mission effectively within the without spending too much money to compensate for delays and such like that.
Great. So as it turns out, as Colby mentioned, it takes 6 years in order to go to Jupiter from Earth, including the flyby. So in order to have enough fuel to make it that entire incredible distance, you need a massive rocket. You need a lot of fuel. So what turns out that based on my research, what we need is the Atlas V, the 551 version is what I would personally recommend for the Hercules mission. This includes one common core booster, which is made out of RP1 rocket propellant, as well as liquid oxygen. This would also include 5 solid rocket boosters powered by aluminum and oxygen, and it's 1 engine Centaur, which is liquid hydrogen and oxygen. Actually, it's very interesting when you see this iconic picture of one example of an Atlas V blasting off. You think of all of this as nasty smoke that is toxic and going to kill you, but it's more likely than not that has at least some amount of hydrogen and oxygen just mushing together and creating steam. There are other factors as well, but in order to get out from Earth's gravity, you need to have quite a bit of fuel. And so all 3 of these different categories, they operate on different stages and they have different purposes, would come together to be able to send our rocket all the way to Jupiter, which is quite impressive. So on the Juno mission, you can see over here, there's a long list. These were the main scientific experiments, and I'm sure there were more that they couldn't quite even put in this list. However, our mission is a Discovery class mission, which means that it doesn't have as much funding as a New Horizons mission. So it wouldn't be able to afford all of these information, all of these instruments. However, that doesn't necessarily mean it needs to. If it's going to accomplish its purpose of understanding IO in more depth, I personally recommend 3 different ingredients, 3 different things that need to be engineered and created. First is a high definition camera for extremely precise imagery, which would just be a camera that you would engineer to have an extremely high resolution, be very precise, have lenses, be very, very high quality. Spectrographs are machines that measure, they use various different techniques to figure out what the substance is, and they can actually be used to figure out what are in atmospheres, like what the different concentrations of different elements are in atmospheres, even just from a flyby. And so these would be 2 of the main goals of mine. But the other main thing that I would recommend is a shortwave infrared instrument, shortwave infrared measurement device. I found this paper that was a peer-reviewed published paper that was talking about if there was ever an IO flyby, this is what we would need in order to really understand what was going on. The infrared wavelength antenna on Hercules-J would be able to measure heat signatures and fully understand like the intricacies of what's warm and what's cold on the surface of Io, even just from flybys as it goes over Jupiter's surface, which would open the door for us to really understand everything there is to know about Io's surface, which would really go a long way for us understanding what exactly is happening volcanically on its surface.
So going off of what you said and building the new technologies, the last trip to Jupiter, Juno, was in 2011. And since then, it's been about 9 or 10 years. And there's something in the technology world called Moore's Law, which every 10 years, the number of the transistors in circuits within the technology doubles. So within that 10 years, the technology has significantly been increased, and we would upgrade the scientific with the latest updates. And then also communications wide, we try and develop that deep space optical communication system. And the first model of this is actually going to take off with the mission Psyche in 2022. So we can see how that works, and then adjust whatever we need to for this Hercules-J mission. And then finally, that new camera, the HerCam, we would update it to have that more high resolution ability. And then it would also take a different orbital path around Jupiter and its moons, because the original Juno cam was designed to go around the poles of Jupiter, and not so much the off-axis path. And then also we would try and get the HerCam to have a rotational ability, which would allow for once we're on site, we can rotate the camera and zoom in and get that high resolution of specific spots, such as like the Great Red Spot. Next slide, please.
Great. And finally, the thing that nobody really likes to think about is the finances of it. I went to the trouble of creating an entire spreadsheet that was talking about the way the mission's budget would break down. This is based off of the modeling constraints in Space Mission Analysis and Design, the Space Design textbook. This is the 3rd edition, which means that it's going to be using statistics that are based in the dollar as if it was in the year 2000. So I had to adjust for inflation between the year 2000 and now. But you can see with the given parameters, with the given instruments and information that it asks for, in addition to factoring in our Atlas V 551 solid rocket booster, we factor all these things in and combine them into one total measurement, and that ends up with about $550 million US dollars today. As I understand it, the Discovery mission has a budget of 500 million. These all come with an error of around 30 to 40%, sometimes up to 50, which means that there are places for improvement. There are places for optimization. And in fact, all of these measurements are the bottom part of this possible range spectrum, because it was my thinking that when actually put into development, if actually sent on to phase 2 and phase 3, where further planning would be required, it would be a top priority for a mission of this caliber, not only to be conducting the experiments that it wants to, but also doing it as efficiently as possible, doing it with as little weight rendered as possible, cutting off additional experiments that aren't quite needed in order to save on weight and time and money. And the main architecture of Juno already having been established, and just sort of stripping that down will also save quite a bit of cost. There's an entire chapter of this textbook that's dedicated to the fact that if you're doing a mission that draws a lot from another mission, then you can use a learning curve as well as multiply a sort of factor that will lower your estimate if it's all of your information is based off of information that's already been created. All of this research, development, and engineering figures actually gets cut by about a fifth after that process happens. So after some research and development, I know for a fact that 50 million would start trickling down, because we already know a lot about what it takes to get to Jupiter, because that was Juno's main mission. We will have learned from Juno's mistakes and be able to grow on them, and hopefully learn more about the way our universe works.
I'm sorry, I guess my bell's being filtered out, but you're a little over 17 minutes now.
Sure. So I think that should be it for us. If there are any questions for us from the panel, then we would be happy to take those into account.
Let me ask you why your mission budget doesn't have any expense for the infrared camera you were talking about.
As it turns out, the spacecraft thermal part here, you can see there's a thermal structure, which includes the weight, which is taking into account, I believe, the thermal sensing abilities of the spacecraft. It also has to take into account its own like heat sinks and things like that. But it's very important for a lot of different kinds of spacecraft to be able to measure different kinds of things. Stop that share.
Okay.
Yeah.
Another thing I wanted to ask you, in your budget, I didn't see anything set aside for reserves. And you find that with space missions, the spacecraft managers, not just the spacecraft, the mission managers always make you have a really substantial reserve as part of your budget. Did you think about that at all?
That wasn't factored into our initial observations, no. The percentage error was a large enough factor that I personally didn't take into account additional extra amounts.
Yeah.
But I can see why that would be a very important reservation, especially for NASA budget people.
Right.
I had, sorry, just as I was about to speak, there's a lawnmower going by, but hopefully you can still hear me. I had a question of just more of a clarification, and I'm not sure if you've planned this far into the mission yet. But you mentioned flybys, but it seems like you are actually hoping/planning to go into orbit around Jupiter. Is that correct?
Yeah, just for clarification, our plan is to use an Earth gravity fling that launches from Earth, it flings off of Earth, gets to Jupiter, and then goes into orbit around Jupiter, and then remains in orbit around Jupiter for some amount of years. Juno has been around Jupiter for over a decade, I think, and so our goal would be to have something that can just fly around Jupiter continuously. This would allow us a lot of IO flybys as as it's going around. It'll be able to access IO from all of its different angles as it orbits and as it sees different coverage of the planet.
Great. And do you have any idea what would be the most limiting factor for how long you'd be able to survive at Jupiter?
Juno specifically was designed to go around Jupiter's radiation intensive areas. It had to go through a lot of testing and measurement and stuff in order to make sure that it was extremely prepared for this intense radiation area. I think that would probably be our main limitation, but I think our main goal would be to create a Jupiter orbit that wouldn't go through those areas as intensely. I'm not sure how realistic that is, considering Jupiter's probably got a lot of that going on, but that would be my main concern, because I think that it would probably be the main sort of limiting factor that would start wearing down on our parts and making our engineering start degrading.
Great, thank you.
Great, thank you so much. I think we have to move on to the next presentation.
Thanks for a great presentation, everyone who spoke on the last one.
Thank you so much.
And I apologize. I think my timing bell is being filtered out as background noise, so I'll just chime in and just tell you what time you're at. So don't worry about that.
Of course. Thank you very much.
Can you guys see this presentation?
Yes.
Okay, perfect. So I'm Cassidy Light. I'm with the Department of Chemistry, and my group consists of myself, Jenna D'Amico, and Alexander Clear, and we are doing the Marine Search and Rescue Satellite System. So kind of an overview of our mission. We are planning to have CubeSats in low Earth orbit that are used to monitor and dispatch aid to watercraft in distress, and this will initially be implemented within the Indian Ocean. It's designed to constantly search for distress signals, and there will be policies mandating that all watercraft will be equipped with, this is actually a radio transmitter, but this will eventually be implemented in all oceans for both watercraft and aircraft. However, due to restraints unrelated to satellite coverage, such as the need for many countries' cooperation, as you will see in our presentation, this cannot occur at this time. Eventually, this infrastructure will be implemented and will be able to expand to more of a worldwide thing, but for right now, we're focusing on the Indian Ocean. The data will be collected and monitored by a new committee within the UN to avoid issues with international waters and to be able to have one entity that monitors these issues and is able to dispatch the aid appropriately. So kind of how it'll work, a boat in distress will send up a signal to our marine search and rescue satellite system, which will then send a signal to our command center, who will dispatch aid, appropriate aid depending on the situation, to the vessel in distress. So this is necessary because the Indian Ocean has had many watercraft in distress situations within the past 15 years, many involving refugees. Some examples, just to name a couple, the 2012 Indian Ocean migrant disaster and the 2009 Indian Ocean migrant disaster. And then what was striking about these cases is that often the vessels signaled for help, but they couldn't be located. So their location couldn't be pinpointed and the aid never reached them in time. The Marine Search and Rescue Satellite System would be able to remedy this issue because they would be able to pinpoint an exact location and the UN would ensure that aid was sent in a prompt manner. So the objectives of our mission, we're going to locate and send assistance to watercraft in distress in the Indian Ocean. And then as a secondary objective, we're going to collect data on the frequency and location of the distress to establish preventative measures and kind of try to curb how many watercraft in distress situations are happening in the Indian Ocean, and maybe to give areas to avoid if there's some rough waters that are consistently a problem. So as our concept, our subject will be radio signals, and the payload of all of our identical satellites will be a transceiver, our communications payload, attitude, determination, and power. Our launch system will involve piggybacking on existing launches happening in around the time that our satellites would be finishing developing. And our orbit would be putting all of our CubeSats into low Earth orbit. And our ground system, we would develop and create a dedicated ground station that would be in continuous operation because watercraft distress can occur at any time. So we're budgeting for 66 CubeSats, which covers the entire Earth, plus launch and maintenance and operations. The off-the-shelf nature of CubeSats leads to a more direct pricing than figuring out things like the aperture diameter and how much that will cause a product to cost. These are just direct off-the-shelf units that we can put into our CubeSat and send up there. So we have a transceiver payload, which are around $7,000 a unit, an attitude determination, which is around $22,000 a unit, a power for $4,000, TT&C for $10,000, and piggybacking on a launch is roughly $40,000 per unit based on what I've seen. And we're also budgeting for a 10-year project, including the maintenance and operations and personnel that goes associated with that. And there are capabilities of expansion. So should we need the project to run longer, or should we need more coverage in different areas like the Atlantic Ocean, the Pacific Ocean? This has capabilities of expansion without needing to send up more satellites. So the total cost for all of this is roughly $151 million. And again, this includes building and developing the CubeSats, launching them, and then their maintenance and operations. So Alexander will be presenting these. Alexander, are you here?
Sorry. Yeah, sorry about that. So our satellites are heavily influenced by the Iridium satellites. the Iridium satellites were meant to enable satellite communication through our voice communication all around the world. But ours is different because we want to transmit SOS signals throughout the world and dispatch aid. So the main key differences is we are basically a scaled down version of Iridium. We don't need as much power. We don't need as much bands, and we don't, or frequency bands, and we don't need as much volume on mass. Next slide, please. So the frequency bands that we are looking at are L and E1, and between 1550 and 1626 megahertz. We chose these bands because they're just outside of GPS frequencies, and we'll talk a little bit more why that's ideal in the next slide. We have about a 1.5 megabits per second data capacity, which is more than enough for a SOS signal. The ground antennas would be a puck antenna, and the actual one on the satellite will be a patch antenna, which means it will need to be directional. Looking throughout the textbook, I found that the antenna itself is about 50 watts, and so a good order of magnitude of safety would be a 90-watt power supply. And have a deployable did someone mute me? Sorry. All right, next slide, please. You guys get that? No? Yes?
Yes, thank you.
Okay, thank you. All right, so the link budget, this was pretty hard for the first time, but the textbook really helped out, as well as some online resources. The gain of the satellite would be around 30 decibels, and the gain of the GPS puck antennas, as seen in the bottom left corner, would be around 3 decibels. So the final link budget value is about 7.3 decibels, which is a decent margin of error capacity. The reason why we chose those frequencies from the previous slide is because this right here is a $20 or $30 antenna piece. So ships already have the capacity to pinpoint their location. So there's no additional infrastructure needed. The shipping companies won't have to buy any special antennas for them to utilize the service. Next slide, please. Data rates, the GPS coordinate and an SOS string is about 30 bits. The actual beacon or GPS beacon would be mounted on the ship itself, but it could also be mounted on the life raft and activate upon hitting water. That way we can not only figure out where the boat sank, but where the people are in the case there's a case of strong current. Also for future reference, we increase the data rate to continuously update the coordinates of the life rafts, possibly have multiple accidents happen at one time, and send help signals to nearby ships that could potentially respond faster. Next slide, please.
Hello, everyone. I'm Jenna D'Amico, and I'm going to be talking a little bit about ground accessibility as well as potential launch vehicles. So each satellite is going to have an orbital period of about 1 hour and 38 minutes with a ground coverage of about 1,000 square kilometers. We'll need approximately 66 satellites, to cover the Earth, and that will be 11 satellites in 6 different orbits, and this data is based on the Iridium satellites. Next slide, please. So as Cassidy mentioned earlier, we are looking to hopefully piggyback on a launch that's occurring in one of the years 2024 or 2025. but for the sake of considering all of our options, we are considering 2 potential launch vehicles right now. Because of the international nature of this mission, we think that it will be ideal to use a rocket from a private company. Currently, we are considering the Falcon 9 launch vehicle from SpaceX or the Pegasus from Northrop Grumman. And here are the following calculations based on those 2 launch vehicles. Regardless, we're going to have a delta V requirement of 5.23 kilometers per second. Using the Falcon 9, an estimate for the fuel mass we'll need is 1,646 kilograms, and for the Pegasus, 4,326 kilograms. And the potential fuel types are solid chemical for Pegasus, or cryogenic liquid oxygen and kerosene with Falcon 9. Of course, there are advantages and disadvantages to both launch vehicles. With the Falcon 9, there's significantly less weight. However, the Pegasus was specifically designed for low Earth orbit, and while it will be a bit heavier, it is also significantly cheaper than a Falcon 9. Next slide, please. Regarding new technology, we are not actually using a significant amount of new technology for this mission. We are using primarily pre-existing technology because this mission is sort of the first of its kind and we don't want to increase the risk. We just want to get something up there that's cheap, efficient, and works. And of course, we plan to optimize pre-existing technology, including the radio beacons that will be used on the watercrafts. Next slide.
So for a timeline for this, we're still in the planning phase, and NASA's timeline of planning to launch for CubeSats estimates around 3 to 5 years, including development and testing. As Jenna mentioned, also, we're looking at piggybacking onto rockets with launch dates in 2024 or 2025. So all launch dates in these years will be considered, and launches in areas surrounding the Indian Ocean will be given priority.
13 minutes.
For potential outcomes, we are considering, regarding potential outcomes, the mission will be regarded as a complete success if all of the following occur. All CubeSats are launched and reach their respective orbits, and 2, communication is established with the CubeSats and all systems function as intended. The mission will be considered a partial success if one of the following occurs. Not all CubeSats make it to launch, but those that do are functional. 2, communication can only be established with some CubeSats. And 3, system functions are mostly as planned, but require tweaking. And the mission will be considered a failure if one of the following happens. CubeSats do not make it to launch, CubeSats do not make it to their intended positions, and communication cannot be established with any satellites. 4, systems are inoperable. Next slide, please. Of course, however, while if everything works, that's all well and good and is successful, we also want our mission to achieve our primary and secondary objectives. So while the space part of the operation is relatively low risk, the collection of the data we get based on these satellites will determine whether we meet our goal of search and rescue. Data will be collected regarding location distribution of rescues, time taken to reach a distressed watercraft, and the frequency of distressed watercrafts and whether it's concentrated around, say, a certain time of year or a certain season. This data will be analyzed by the UN and compared to existing data. And if the satellites prove to present watercraft losses, the prospect of future missions implemented in the Pacific and Atlantic Oceans are a potential. And if there's no significant prevention of watercraft losses, the data collected as well as the assessment of the mission will be valuable in assessing future search and rescue programs. And of course, we also have to note that there are a lot of sources of error in our data. For example, if we're focusing on migrant disasters, we have to take into consideration that some of those watercrafts might not be registered, so they might not have the appropriate radio beacon on them. So this will all be analyzed and determine whether our mission meets its primary and secondary objectives. Next slide.
Previous missions. So the most notable previous mission are the Iridium Next satellite constellation. As I said earlier, this is a satellite constellation that links voice data together. So through satellite phones, it also connects airplanes together or any aircraft together to allow to talk to each other and the ground station. And it's already, the most recent launch was in 2019, and it was owned by Motorola, but is now owned by Thales Alenia Space Corporation. Next slide, please.
Coming up on 17 minutes.
The previous mission that I took a look at was Starlink, and Starlink is a constellation of satellites being constructed by SpaceX meant to deliver internet globally by 2021. And since we're over on time, I'm not going to get too into it, but there's a lot of controversies about Starlink. There's a lot of controversies about how satellite constellations will affect current and future space infrastructure. So of course, when we're designing our mission, we have to take these into consideration to hopefully mitigate our effect on other space missions and space infrastructure. And one technology of interest with Starlink is they have technology meant to autonomously avoid collisions in space. So of course, we'd like to look into that. Next slide.
So just in conclusion, our marine search and rescue satellite system can potentially modernize our current search and rescue satellites and save lives. The use of pre-existing technology will minimize the risk of the operation, and radio wave communication in low Earth orbit guarantees efficiency. The success of this mission can have the potential to have a worldwide effect on policy and search and rescue standards. And then our references. And that's it.
Any questions from the panel?
Yeah, I've got a question. So how well does the constellation have to be able, how well does it have to be able to identify the location of the boat? Just, I guess a different way of asking the question is, within how many miles does the satellite need to be able to report a location in order to be useful for search and rescue?
So I'll handle that one. So basically, it really depends on the cost and how high-end the antenna on the ground is. Since it's a GPS chip, it has the potential to get within a meter, but some lower-end chips, it's like 10 meters. But it's 10 meters on the ocean is not such a huge deal where you wouldn't find somebody if you're tens of meters away. So because it's GPS, it's pretty precise. Mm-hmm.
I had a question. Given that you're in low Earth orbit, are there places in the out in the Indian Ocean where I think you said you had about 1,000 kilometer visibility on the surface of the Earth? Are there places out in the middle of the Indian Ocean where there wouldn't be a ground station available to communicate with above the horizon?
No, we should be okay with that, especially because we were planning on having a single dedicated ground station facility, but with that we could have multiple different like locations that would connect with. So I guess it really wouldn't be a single ground station, but yeah, we would ensure that communication was had at all locations that were necessary.
Yeah, part of the challenge of this mission is that it's international and there will be a lot of international cooperation in politics required, but we are looking for ways to effectively do that.
Yeah, I had a question about that. I really like the idea of sharing this responsibility and like saving lives, but I'm curious about if there's any precedent for a project like this with so many different countries cooperating and sharing a resource. I didn't know if you guys looked into that. I know it's beyond the like science aspect of the launch, um, but I didn't know if you had seen any examples in the past that might give you an idea of how to get the human elements of your project to function as intended.
So we haven't really seen much. This is pretty much an unprecedented mission with so much international cooperation in space. But something just off the top of my head, like the International Space Station, multiple countries inhabit it. Like it's a small scale example of international cooperation. And we believe that involving the UN in the development of this project will kind of ease that transition and make it a lot easier for international cooperation to occur.
Great, thank you so much for the great presentation, and also thank you very much for the feedback from the panel. So now I think we move on to the next presentation.
Hello, everyone. My name is Max Barton. Our mission is on Saturn's rings. The other members of my group are Mohammed, Landrea, and Alexis.
All right, so before we delve into the details of the mission, I'll go over some background information and talk about the rings of Saturn. So Saturn basically has the most extensive ring system of any of the planets of the solar system, which is much more extensive than Uranus, Jupiter, or Neptune. The rings are basically divided into different sections based on their densities and distances from the equator of the Saturn. They span from about 7,000 kilometers to about 80,000 kilometers and vary in thickness, ranging from 10 meters to almost 1 kilometer. The rings mostly consist of ice and water ice and have some impurities in smaller quantities with particle size from 1 centimeter to about 10 meters. There are gaps in the middle of the rings which arise due to various reasons, including the gravitational pull of Saturn's moons or passages cleared by tiny moonlets, among other factors. These divided sections I mentioned earlier are categorized from A to G and some other sections, with A, B, C being the closest rings to Saturn and E, F, G being the outer rings consisting of water ice. And these outer rings are the ones that are of interest to us. Next slide, please.
So our main goal is to collect 5 kilogram samples from each of the 3 outer rings, E, F, and G. To do this, we were going to mount a particle collector on the tip of an extendable boom. We'd use the boom also for our magnetometer, but the boom would allow us to keep our main spacecraft away from any hazardous debris. In order to collect a 5 kilogram sample, we think we would need to sample a decently large area of the outer rings. Based on the inner ring's density of up to 100 grams per square centimeter on the surface, and commonly down to about 30 grams per square centimeter, we think the outer rings would be much more spread out, and so close to 500 square centimeter of the surface would need to be covered in order to collect 5 kilograms. Also, on the outermost ring, it is extremely wide comparative to the other rings, and so we're not sure if we actually would be able to collect a sample or if it would be so spread out that it would be hazardous to get close to the ring. Next slide. Our secondary objectives would be, well, I suppose this would be part of the primary, but to return those samples to Earth for characterization, we would look at age, chemical composition, and origin of the samples. This would allow for weight to be cut down on the spacecraft and keep it low cost, and also would give a more in-depth analysis of the samples. We also hope to measure the gravity field, magnetic field, and physical characteristics like the depth and surface density of the outer rings, and collect images for the spokes of Saturn's rings. Our trajectory includes flybys on the way out and the way back of Jupiter, and we hope to image Jupiter's Great Red Spot during that. And we are considering passively collecting samples between Jupiter and Saturn. This would just be having the particle detector exposed as the spacecraft travels, and not using any excess energy to collect the samples. Next slide.
So now that we know what, or that we have presented you guys with what our ideas are, we can compare it with previous missions that have gone to study Saturn. So the Cassini mission was an orbiter mission that consisted of delivering a probe to Titan, and then the orbiter would remain around Saturn so it could study the planet and its rings and satellites. So the objectives of the Cassini mission were to determine the 3D structure and dynamical behavior of the rings, determine the composition of the satellite surfaces, determine nature and origin of dark material on Iapetus's leading hemisphere, measure the 3D structure and dynamical behavior of the magnetosphere, study the dynamical behavior of Saturn's atmosphere at cloud level, study time variability of Titan's clouds and hazes, and characterize Titan's surface on a regional scale. So the Cassini mission was really focused on Titan, and then the Voyager 1 and 2 missions were a pair of spacecrafts launched to explore planets in the outer solar system. So each Voyager mission, the objectives were to investigate the circulation dynamic structure and composition of the planet's atmosphere, characterize the morphology, geology, and physical state of the satellites of the planet, provide improved values for the mass, size, and shape of the planet, satellites, and any rings, and lastly, to determine the magnetic field structure and characterize the composition and distribution of energetic trapped particles in plasma. So the Voyager missions were focused on the planets themselves. So our mission is really focused on the actual rings of Saturn.
So as with any other mission, one of the main logistical concerns we had to consider was what launch vehicle and propulsion system would be best suited for this application. For a launch vehicle, we thought it would be best to use the SpaceX Falcon 9 model. It's a pretty standard two-stage system powered by vacuum engines, but its biggest advantage is its low cost compared to some of its competitors. This would allow us to especially considering that there is a budget constraint, this would allow us to put more of our budget towards our scientific payload and other aspects of the mission. And it still provides more than enough thrust to get us into any orbits necessary. What was a bigger concern to us was choosing a correct propulsion system for this mission. We decided that one of the best options would be a xenon-based ion propulsion system. This system utilizes the ionization process to create a plasma, which is then expelled to create thrust. And xenon particularly is useful as it's under normal conditions is a very stable gas, but it possesses an ionization energy that's low enough that ions could be created without needing a lot of initial starting energy. And additionally, it's a fairly well-established technology. It's currently being used in over 100 geosynchronous satellites, and it was also used on the Dawn asteroid explorer missions.
So inside of the xenon ion thrusters, we need to carry a lot of fuel. Our initial thought was to use the N-star ion thruster, and we'd need about 16 kilometers per second of delta V to get to and from orbit of Saturn from low Earth orbit. The N-star has a specific impulse up to 3,100 seconds. And with that, we'd need almost 0.7 kilograms per kilogram of spacecraft, which is quite limiting, especially when the N-Star can only carry about 2/3 of its weight in fuel. Excuse me, it can carry twice its weight, twice its dry mass weight in fuel. So looking at alternatives for that, JAXA's Hayabusa 2 uses a smaller engine that would need more xenon per kilogram of spacecraft, but it requires a lot less energy to power it. And the opposite direction would be NASA's evolutionary xenon thruster, which is 3 times the size of the N-Star, but with that requires so much more energy to power the thruster.
So one of the more difficult parts of designing this mission was trying to figure out what the best launch and trajectory logistics would be. And as it doesn't come as a surprise, the process of both reaching Saturn and returning would require a multi-phase trajectory over the course of many years. So our outline below are our theoretical timeline for this. So we would hope to first launch in 2037 into a low Earth orbit to begin, and this year was very intentionally chosen such that the spacecraft would have enough time to reach Jupiter, where it would perform a gravity assist. While Jupiter and Saturn are closest together, such that the spacecraft had to travel the least amount of distance. So after this low Earth orbit, we performed the orbit transfer with a trajectory towards Jupiter. Based on the Voyager missions, we estimate that this would take roughly about 3 years. From there, we could perform a gravity assist off Jupiter to get to Saturn and enter Saturn's orbit. We were hoping to then adjust it to make sure we were orbiting parallel to the rings, which will be important for particle collection, as was mentioned earlier. And while we weren't able to find too much published information about missions that are going out to this part of the solar system and returning to Earth and what their trajectory would be, we theorized that we would be able to repeat this process in reverse to get back to Earth. So going from Saturn's orbit to Jupiter's and Jupiter's back to Earth. And on the way back is when we would aim to do any potential imaging of Jupiter and its great spot, so that we wouldn't miss any of the favorable alignments between Jupiter and Saturn.
11 minutes.
As far as scientific instrumentation is concerned, most of the instruments that we were hoping to have on the spacecraft are fairly well established, but we are proposing one new technology. Among the established instrumentation, we would want an optical navigation telescope similar to the one used in the Hayabusa 2 mission, to help the spacecraft navigate, especially as it's close to the rings. We propose having both visible light and IR camera for any imaging that we hope to get done. As mentioned earlier, we would have a magnetometer, since it is known that both Jupiter and Saturn have some very interesting magnetic fields associated with the bodies. We would hope to have cosmic dust analyzer similar to the one used within the Cassini missions, but we'd have to adjust it for our purposes, especially since there would be that passive portion of it. And while we don't particularly plan to have a direct instrument for calculating gravity, we were hoping that any interesting gravitational properties could be back calculated based on how the bodies affect the trajectory of the spacecraft. Our one new technology we're proposing is our particle collection mechanism, and there were a lot of things that we had to take into account when trying to figure out the best way to do this, including the fact that Saturn's rings do consist of many particles that are electrically charged. They are various sizes, traveling various speeds. And since we hope to sample from the outer rings, which are known to be a little bit less dense, we were hoping to use some kind of boom mechanism which would extend over the surface of the rings and collect particulate dust matter, and would be able to be drawn back into the spacecraft to hopefully be returned to Earth for further analyzation.
So for the communication architecture for our mission, we would use a high gain antenna, which is pointed towards the Earth, to be able to send data. It would use 3 radio wavelengths, so a 14 centimeter wavelength in the S band, 4 centimeter wavelength in the X band, and 1 centimeter wavelength in the Ka band. The mass of the antenna is about 14 kilograms, and the peak operating power is about 81 watts. It takes about 68 to 84 minutes for radio signals to travel to Earth to the spacecraft and vice versa. Obviously, ground controllers can't give real-time transmission, but since the main point of our mission is to collect samples which are going to be returned to Earth for to be analyzed, it's not super important for this mission except if something is going wrong. And we plan to use a established ground station, which is the Madrid Deep Space Communications Complex, which is intended for deep space missions. So this is how we can have two-way communication with Earth. And then also for the power supply, power will be provided to the spacecraft through the use of 3 radioisotope thermoelectrical generators. So each of the generators can decay 10.9 kilograms, or since we're using 32.7 kilograms of plutonium dioxide, which will generate electrical power to be used throughout the spacecraft. At the beginning of the mission, each RTG is capable of producing 300 watts of electrical power, and towards the end, the efficiency kind of reduces, so it'll be able to do 210 watts, which is fine because as we saw on the previous page, the for like data transmission, it only takes about 8 watts, 80 watts of power, sorry. And for the fuel for the spacecraft, we would use, since we're using a Falcon 9 full thrust, it will use RP1 and cryogenic propellants, such as liquid hydrogen and oxygen. And RP1 is just a highly refined form of kerosene, and the 9 full thrust is capable of holding 518,400 kilograms of fuel.
Just over 15 minutes.
All right, so one of the advantages of bringing samples back to Earth is that we can use much more sophisticated technology available here to analyze the samples than we can through imaging and just spacecraft. There's a lot that is unknown about Saturn and its rings, and the samples can help us maybe answer some of those questions. Saturn's rings have been disappearing, and they also cause rain on the planet, and we can estimate how much time we have before they completely disappear and why they're disappearing so quickly in the first place. We might also be able to answer whether these rings were formed during the planet's formation or were these acquired later. Dust samples and their weights and densities could tell us about how they were formed and how old they are, as the dust is similar to the rings of debris that formed the entire solar system. Also, an interesting question that Sassini raised was the mixing of the upper layers of Saturn's atmosphere with these rings, and the samples that we obtained through this mission could help us explore this aspect as well in further detail. Next slide, please.
So for our budget for the mission, we used an algorithm from, it actually was from Texas A&M University, that gave us the opportunity to account for using old equipment and not having to newly develop all of our equipment. And so that helped cut down on the development and production. And using, with the Falcon 9 full thrust, the total cost ends up coming to just under 500 million, 460 million, which leaves 40 million for unexpected costs. Whether that would be enough or not, we're not sure, but yeah.
17 minutes.
Okay, these are our references. I'll stop sharing.
Are there any questions?
This is Kevin. I had a question. Do you need to bring your samples back at cryogenic temperatures, or will you need to maintain temperature control all the way back to the Earth and back to the ground?
We were not planning to do that. Whether as the development proceeds, whether they decide that they want that or we decide we want that, the challenge seems like it would be with re-entering the atmosphere. How do you possibly keep it cold enough? But so yeah, we're not really sure about that.
You might be able to retain the dust components, but you might lose any volatile ice components.
Yeah.
When on the same idea, you talked about collecting 5 kilograms. What percentage of that 5 kilograms would in fact be particulate, do you believe?
We do not know. from Mohammed's first slide, it seemed, well, it seems like in the outer rings, up to 90% is ice. So it
yeah,
might
so
end
at
up
the
being,
outer rings mostly have like particulate. They have like most of it is like water ice. So pretty much all of it is going to be water ice samples, and there's just some other abnormalities that we're not really focusing on. We're mostly concerned about the water ice.
Mhm. But of course, you want to analyze the particulate matter, not the water ice. And so the question is, what percentage are you going to be getting enough in that 5 kilograms?
we're not sure. As the inner ring F is a lot more dense, so it would have more particulate matter, which is why we weren't too concerned if E is too spread out. If we couldn't sample E, then it wouldn't affect it very much. But also, if we decide it wouldn't be enough, we could move in to the inner rings like G, or not G, A, I think is the next ring in, and it's much more dense and would have a lot more particulate matter in it.
So you wanted to do, sorry, Kelsey, go ahead.
No, you go, Elizabeth.
Okay. Yeah, you wanted to sample both Jupiter and Saturn's rings, right?
No, just Saturn.
It was just Saturn. Okay, never mind. My question's invalid. Go ahead, Kelsey.
Okay, well, I know we probably have to move on. I just wanted to say I liked your consideration of the safety of the spacecraft while you're sampling, and I know you could develop that more in the future, but I just wanted to say I thought that was good that you took that into account.
Thank you.
Great, thank you so much for the presentation and great feedback from the panel. So now we are moving into the last but not the least presentation on Venus atmosphere, magnetic mission.
Hi everyone, my name is Serena Flint. I'm from the Department of Physics and Astronomy.
My name is Mohammed. I'm from the Department of Mechanical Engineering.
Hi, I'm Chris. I'm from the Department of Earth and Environmental Science.
And today we're going to be talking about the Venus Atmospheric and Magnetic Mission, or VAMM. So what exactly are we interested in studying over at Venus? Well, our primary goal is to further study the interaction between solar wind and Venus's atmosphere by parking the satellite in a Sun-Venus Lagrange point. And given our positioning, we're also in an ideal place to more generally and continuously study cloud cover and the atmosphere of Venus. Since Venus will usually be in different parts of its orbit than Earth, this will also present us the opportunity to collect more data on solar wind conditions and potential storms for space weather predictions, like over SWEPC. So why is it important that we send another mission to Venus? Well, a recent mission to Venus, Venus Express, directly observed a phenomena called magnetic reconnection for the first time at Venus. And it was actually quite different than what we study here on Earth. And it's important that we gain more data to understand these differences, and because magnetic reconnection itself gives us insight into how energy is transferred into the atmosphere. But we'll talk more on this later. By positioning our satellite, by positioning our spacecraft in the magnetic tail, it also gives us the unique opportunity. I'm sorry, hang on. By positioning our spacecraft in this area, it also gives us the opportunity to study reconnection in the magnetic tail, and it also allows us to study the non-thermal escape of hydrogen and oxygen ions in Venus's atmosphere, which in turn allows us to give us a better idea on the evolution of Venus's atmosphere over time. Aside from that, what makes our mission unique? Well, for starters, it's not going to orbit Venus per se. We're just going to park it in a Lagrange point. This allows us to take continuous measurements without gaps in regional coverage and eliminates biases due to positioning or angles of observations. Most of the popular Venus missions follow highly inclined and elliptical orbits around Venus, and from that we suffer from short windows of observation and gaps in our coverage. But above all, in all of my research, I couldn't find a single long-term mission outside of Earth that utilized the Lagrange point. This mission will hopefully prove that this is a viable option for missions in the future, and if not, then I guess now we know. But yeah, let's take a step back before we talk about how we take the data. I mentioned magnetic reconnection, but I assume that we don't all know what magnetic reconnection is. So first of all, we need to talk about, does Venus even have a magnetosphere? Well, technically yes, but it's not caused by rotational dynamo like we have here on Earth, caused by the molten core. Venus has a very dense carbon dioxide rich atmosphere, and it's dense enough that when solar wind interacts with it, it gets deflected around the atmosphere. And that in turn forms a very weak induced atmosphere, and it's like 10 times weaker than our own magnetosphere. So then this goes, what is magnetic reconnection? Well, sometimes solar wind can cause the magnetic field lines in the magnetotail, which is kind of the long tail behind the planet that you might see in diagrams like this one. It causes them to snap and reconnect. And on Earth, or at Earth's magnetotail, this causes a tremendous amount of energy to be sent into the magnetic poles. It's actually the reason why we see the aurora here on Earth. But in Venus, this energy just gets sent into the night side atmosphere. So why should we care? Well, it's so different than what we see on Earth. Even the shape of the magnetotail and field lines we observe are just so different and much more shallow. And we don't know a whole lot about this process at Venus and what the differences may be. And obtaining a better understanding of the process and these differences will give us a more comprehensive picture of how energy gets transferred into Venus's atmosphere and the subsequent effects of it doing so. And without further ado, here's how we plan on taking our data.
All right. So we took a lot of inspiration for our scientific payload from the Venus Express mission. In particular, when we're studying the magnetosphere, the Venus Express use something called a fluxgate magnometer or magnetometer. And we thought that this sort of technology would be good to use because not only is it proven and reliable, but since it's existing technology, it might help reduce the cost for this sort of riskier mission. What the fluxgate magnetometer actually does is it takes measurements of the magnetic activity in the magnetosphere and in the magnetotail. It has two sensors, an electronic suite, and it studies the interactions between the plasma environment from the solar wind and the induced magnetic field. And then in addition, we would also include some spectrometers, some IR and UV in particular. These would help not only study the atmosphere composition and environment, but also potentially the surface of Venus. And in comparing like the different layers of the atmosphere, it could help us to understand how exactly the interaction between the ionized layers and the solar wind actually affects the entirety of the Venus atmosphere. And again, these sort of spectrometers were present in Venus Express. So once again, we're taking existing technology just to lower risk of the mission. Next slide. Okay, so also we'll have something called a multi-wavelength imager. This sort of imager was used in missions like the Akatsuki mission from the Japan Aerospace Exploration Agency. What this does, it will image the Venus's cloud cover, which is useful for us because of the relation between the upper atmosphere and the magnetosphere on Venus. Hold on. Sorry. Yeah, so this will also help us look at the solar radiation and how that's being reflected and dispersed around the atmosphere of Venus. And then finally, we'll have something called a hot plasma composition analyzer. And what this does is it actually analyzes the mass and type, or the plasma mass and type in the magnetotail. And this instrument is also recycled from the magnetic multi-scale mission. Sorry, can you hear me?
Yeah.
Okay. Yeah, this is useful for us because we want to the plasma relations with the ionized layer of Venus's atmosphere are particularly fascinating for this sort of induced magnetosphere phenomenon that we observe. Next slide. Yeah, so why are we looking at any of this? Well, on Earth, like Serena was saying, on Earth, the Earth's magnetosphere is much different. It's not induced by the solar wind, but there are still some potential similarities that we could study with this unique environment. For one, do we need to go back one? Oh yeah. Serena, can you go back one slide?
I think there might be a slight delay because now I think we were looking at the slide that's titled "What are we looking for?"
Yeah.
Okay. Thanks.
Thank you. All right. So yeah, like I was saying, while Venus obviously has a very different magnetic sphere environment than Earth, there are slight similarities that could potentially be interesting to research. And like we said earlier, the atmosphere of Venus is very heavily carbon dioxide rich, and so studying how that sort of atmospheric environment reacts with solar wind and plasma could potentially be interesting for practical uses on Earth. So like on Earth, our magnetosphere is primarily influential on our communications networks and other sort of satellites. And so changes in that sort of environment are important for us to understand moving forward. So yeah, I think that is that slide. All right, you can move forward, Serena.
Okay. So how are we going to get there? Well, we recommend a launch date of May 1st, 2027, which results in Venus rendezvous on July 23rd, 2028. This maneuver would be a standard geosynchronous transfer and would have a delta V cost of only 3.5 kilometers per second from a geosynchronous orbit. So we have to factor in that there's the extra delta V cost of getting it into that orbit. If a delay is anticipated, it's also possible to launch a year later on October 20th, 2028 for Venus arrival on January 12th, 2030. Further postponements would be considered on a recurring 583-day basis, just based on how the orbits of the two planets align. However, it would jeopardize moving the mission over our proposed budget for additional operational costs. As highlighted before, unlike most missions we see, we propose that the mission that we position the spacecraft into one of the Sun-Venus L1 or L2 Lagrange points. We would do so by, once we get to the rendezvous with Venus for a rather small delta V cost, we can then maneuver the satellite into one of the points. And we can orbit into either point. I think I would recommend L1 at first, but the choice is arbitrary. So the L2 Lagrange point would be favored for taking measurements of the magnetotail and studying the inherent relationships between the solar wind and the atmosphere. So if we're looking at the Sun, Venus, the L2 point is behind Venus, and the L1 point is in between the Sun and Venus. The L1 point would be favored for solar wind and cloud cover analysis. However, given that the cost for transferring between the 2 points is so low, it's entirely possible to designate periods of the mission, and I highly recommend that we do this. We switch between the 2 points so that we can get we can utilize the full scope of the mission. And the maneuver is estimated to only have a delta V cost as little as 6 meters per second. There's an example trajectory calculation I found in a paper specifically for a 2031 Venus rendezvous. However, there's infinite possibilities. It's worth noting that the L1 and L2 Lagrange points are located in local potential maxima, and therefore they're classified as unstable Lagrange points. However, experience for missions in the Sun-Earth L1 and L2 points show that yearly upkeep to maintain the proper positioning is not costly. It's only 1 to 10 meters per second per year, and therefore we shouldn't be concerned about it.
Right. So the launch of communications, we'll be using the Falcon 9 to, send VAMM up to Venus, and the communication architecture we'll be using a 3 high gain antenna. So again, because of the previous Venus Express mission, we'll be basing our communication off of the instrumentation and communication off of that mission. So the 3 high gain antenna, which has a pretty transmission rate of what we want, 256 kilobytes per second, and then 8 GB cache, which should be able to send data back in a timely manner. And then ground communications will be managed by NASA's Near Earth Network. Next slide, please. So a little bit about the power system and the propulsion. So we'll be harnessing the awesome power of the sun to sort of power our VAMM. And it will be using 20 meters squared of triple junction gallium arsenide technology based solar panels. And these are the current, standard or like that efficient sort of solar panels that a lot of space missions are using. And so this will provide around 9,520 watts at full exposure, which is ample amount of power to power both the propulsion system, which works at a maximum 4.5 kilowatt, as well as the instrumentation that we have on board, as well as our communication equipment. And so this sort of kind of configuration of using solar panels with the SPT-14, the stationary plasma thruster, has been tested, is slated to be used on Psyche, as well as a Europa Clipper. It was using the Europa Clipper. And so this will be, I guess, the
14 minutes. Sorry about that.
Power system of choice at Lagrange point L1, but at L2, since we're behind Venus, we'll be using a radioisotope thermoelectric generator as sort of our secondary power source. A little bit about the propulsion system. It'll be like I said, the stationary plasma thruster 140. It's a tried and tested technology. And the good thing about this is it minimizes the weight, that portion of the weight that's going to be attributed to the propulsion system, because it only weighs about 8 kilograms. And given how low our delta V is, even switching between L1 and L2, this was an optimal kind of propulsion system. Next slide, please. A little bit about the budget. So our budget, while our instrumentation and a lot of different aspects of our missions were based on Venus Express, the budget was based on Mars Express, because Venus Express was based off of the Mars Express mission, and so we just sort of recycled the budget and sort of adjusted it. So for example, the Mars Express mission used Soyuz frigate configuration to launch with a higher payload than what we need. So we stripped that down. We sort of removed the launcher, the lander part. So we took out the lander aspect of that mission because we're not landing on Venus. And then we adjusted for like a different payload. We have a lower payload because we have less instrumentation. We have a smaller propulsion system. And we sort of adjusted. We added an additional sort of $10 million to account for the change in propulsion system and instrumentation, as well as our solar cells, which brings our total budget up to about $248.9 million. And we're using the Falcon 9 launch system, which is different from the Soyuz frigate. So that's slated at $68.79 million. However, that is a new rocket. If you use a recycled Falcon 9, that is about $50 million. So that's about $18.79 million saved if you use a recycled rocket. So there's plenty of wiggle room in the budget. We can both save money and spend more if need be. And yeah, that's pretty much it. Do you guys have any questions?
Yeah, sure. I was curious about the instrument, the FluxGate magnetometer that you said has heritage from Venus Express. And I was just wondering if how your trajectory and location are going to compare to Venus Express, and if there's any differences in how the instrument was designed based on how close it was to Venus. That would be important for your different design.
I can take a shot at this.
Sure.
Or Chris. Okay, I can. So Venus Express was one of the missions that had a highly elliptical orbit. So at its abasis, if I'm remembering that word correctly, at its furthest point in its orbit, it was very far. So I believe we had talked this over in the group. Chris can maybe elaborate on this more, but based off of that, it was still operational at its furthest point, and like it was really far. Chris can probably give you a better idea of what those numbers were. We think that it will be perfectly fine.
I believe Venus Express furthest point was around 14 million kilometers from Venus. And the Lagrange points that we're planning on parking at would be, I believe, like around 1 million kilometers. So substantially closer. That's part of the reason we chose these instruments, because they're proven in this mission that kind of varied in range. And so theoretically, they should work at these ranges.
Great, thank you.
I have a quick question, just coming at this from sort of a layman's perspective. I think the idea of using the Lagrange points is really interesting, but I was wondering, are you guys aware of a reason why that hasn't been something that previous missions have used in the past?
So that's a really good question. So I couldn't find a particular reason why they weren't used. So kind of the whole idea behind this mission, why I got this idea, is I originally wanted to do a mission to study the poles of the sun, but solar orbiters are already doing that. So I found this really interesting paper that was kind of arguing in favor of, let's study Venus, let's study how the solar wind interacts with its atmosphere, but we should use a Lagrange point. And the whole paper is arguing as to why we should do it. They have tons of numerical calculations of proving how the orbit is stable, proving that there aren't any reasons as to why it shouldn't be done. And I couldn't find any particular reasons either. If any of the panelists have any comments, that would be cool to hear, but I can't think of any reason.
I have a potential guess. So based on the orbital distance that you're describing for the Lagrange point, it'd be really hard to do any surface imaging. And so if you're trying to do anything where you're trying to resolve geological features on the surface of the body, you may run into challenges trying to do so from that distance.
That makes sense.
Though, of course, it's a little hard to see the surface in Venus's case in any event because of the cloud cover, the opacity.
There's some CO2 windows through which you can see.
Yeah.
Awesome, thank you guys.
Great. So I think we are reaching the final time. So first of all, I'd like to thank you all the students for giving wonderful presentations. So great job.
Good. Yep.
And I also like to thank the panelists for being here and providing very great and constructive feedback. And if we just run out of time, please feel free to email me the feedback that I'll be happy to pass on to the students. And I also want to thank Scott and Stephen for being a TA for this class, and thank you very much for supporting throughout the course. And the final results will be announced after I collected the reviews, so stay tuned. And again, thank you so much, and I really enjoyed the whole experience, and I hope you also enjoyed as well. And this is the first time to teach this class for myself, so I'm also looking forward to any feedback, so that will be appreciated. And this concludes today's final presentations and the formal part of this class. So thank you very much for coming. Thank you.
Thank you, Mickey, for organizing all this.
Thank you.
Yeah.
It was fun.
Nice to meet you all.
The presentations were great.
They were.
Thank you, Judy.
Yeah, great job,
Elizabeth,
everyone.
Aaron, Kevin.
You could see your hard work.
Thank you guys. Really appreciate
Bye.
it.
Thank you all.
Bye. Have a good one.
Thank you.
Thank you, Professor. Thank you for everything.
Thank you. Thank you, Mohammed.
Thank you, everyone. Thank you, Professor.
Thank you. Thank you, Alex.